Remember, they are also different hours, no?
With just one talk, so it's not a session, it's just one talk with Piotr that is gonna talk about fermionic magic resources of quantum many-body systems. Please.
Thank you. Okay. Hello, everyone. First of all, I would like to thank the organizers for putting up this nice event and giving me this opportunity to present my work. And the topic of my work is quantum magic, something which is called quantum magic.
It's not working.
It stopped working. Let me see. Maybe if I click. Okay. Okay. It seems to be working. So this is concept which is a bit orthogonal to what is typically considered in this workshop. So I would like to introduce it in quite a broad way, and then I will be talking about many-body systems in and out of equilibrium. So let's start with magic to understand what quantum magic is. So if we think about magic as we know from fairy tales, it is something which allows one to do extraordinary things. For instance, if we consider story of Pinocchio, it's a story of a wooden puppet, which, thanks to magic of Blue Fairy, became a boy. So magic here is a resource which enabled some unusual thing to happen. And now let me consider system of n qubits. And then typical states of n qubits are just these very dull superpositions of 2 to the n states. However, there are two sets of states that will be focal points of my today's presentation, and these are stabilizer states and fermionic Gaussian states. Both types of states share the feature of being efficiently simulable, efficiently meaning with resources scaling polynomially with system size on classical computers. This means that if state of some quantum device is stabilizer state of fermionic Gaussian state, it is an ordinary wooden puppet. It has no power in it. In order to have power, we need quantum magic, which makes the states interactable for classical computers, which means that once we have some quantum magic in state, we can think that there might be useful use cases of quantum computers beyond what can be done on classical computers. So that's the motivation to consider quantum magic. And then my focal point of the talk will be ways of quantifying this quantum magic. And the language which enables that is the language of quantum resource theories, which is very general framework. And then the most successful quantum resource theory, or most fundamental, is the resource theory of entanglement. Here I will be focusing on those two classes of states, stabilizer states and fermionic Gaussian states, and I will be building resource theories of non-stabilizerness or fermionic non-Gaussianity, which will be the resources that describe the deviation of given state from this classically simulable set of states. And in order to build such a resource theory, we need to specify what are free states, what are the states that are that belong to our sets, what are the operations that are allowed to transform the states, to transform state from our free state to another free state. And then there will be other states that are beyond the sets of those free states are resourceful states.
Sorry, Piotr, a question that perhaps is not fully related. I mean, Gaussian, let's say, fermionic Gaussian states are very, let's say, easy to understand from a physical point of view. You have a quadratic Hamiltonian, and stabilizer states are never so, let's say, so straightforward from a physical point of view. There is a corresponding, like, I start with a simple Hamiltonian and I construct them in that way, or no?
Yeah, so this is what I'm heading to.
Okay.
Since I wanted to do a broad introduction, I I will describe briefly stabilizer states and why they are efficiently simulable on classical computers. So, so this is exactly my next slide. So let's consider system of n qubits, and then we can think about some circuits acting on these qubits. We have Pauli operators acting on each of the qubits, and we can construct Pauli strings, which are tensor products of these operators. Each Pauli string can be parameterized as a product of x and z operators to power 0 or 1 acting on the subsequent qubit. In total, we have 4 to the n Pauli strings, which span the basis of the operator space acting on the system of n qubits. And now Clifford unitaries, Clifford operations are unitary operations, are a subgroup of unitary group such that they map single Pauli string to another Pauli string. And this is the defining feature of Clifford unitary. This means, and then stabilizer states are states that are obtained from computational basis state 0 by action of Clifford unitaries. When we use this condition that Clifford unitary maps Pauli string to Pauli string and observe that 0 state is state which is stabilized by Z and by Z operators, meaning that it is eigenstate of Z operators to eigenvalue 1, then by simply by transforming the eigenvalue equation Z times 0 equals 0 with Clifford unitary, we will get that the stabilizer state is eigenstate of Pauli strings that come from conjugating Z operators by this Clifford operation, which means that our Pauli string, our stabilizer state is an eigenstate of a set of mutually commuting Pauli strings, and each of these Pauli strings can be parameterized in that way just by set of zeros and ones, and this gives us full description of this stabilizer state. So in order to encode stabilizer state on a computer, we just need to represent those Pauli strings. So we need just a bunch of zeros and ones. The numbers of zeros and ones scales polynomially with system size, quadratically with system size, and then if we want to perform operations on stabilizer states, those will be the operations that that map stabilizer states to stabilizer states. So this condition is always fulfilled, and in that way we can simulate stabilizer states on computer efficiently. And then stabilizer protocols are not only Clifford unitaries, which map stabilizer state to stabilizer state, but they can also include more operations such as computational basis measurements or tracing out some qubits, and then they still map stabilizer states to stabilizer states. So the result that this can be, this is the reason why they can be simulated classically, and then this result is known in literature as Gottesman-Knill theorem and can be used to build efficient classical methods of simulating stabilizer states. And then they play important role in quantum error correction, but then the stabilizer states also feature interesting many-body phenomena. For instance, measurement-induced phase transitions, which are transitions in the properties of state that is evolving under action of unitary Clifford gates and computational basis measurements. If we are doing a lot of measurements, the state ends up in a real phase in which the entanglement, bipartite entanglement in that state is following area law, and there exists a critical measurement rate below which the state features volume law of entanglement, and then there is a transition between the two regimes. This is one example of interesting phenomenon that can be seen with with Clifford circuits. So that's one of the groups of free states and free operations: stabilizer states and Clifford unitaries and stabilizer protocols. And that is relevant for the Richard's theory of non-stabilizerness. And then the other thing is fermionic Gaussian states. So basically, I am thinking now about still system of n qubits for which I am defining 2n Majorana operators, which are again Pauli strings known from Jordan-Wigner transformation. They anti-commute. They can be used to build Dirac fermions. And fermionic Gaussian unitaries are unitaries that are quadratic in Majorana operators. Since the Majorana operators anti-commute, the most general expression here involves matrix H, which is antisymmetric. And similarly, as acting with Clifford unitary on 0 was giving us stabilizer states, fermionic Gaussian states, pure fermionic Gaussian states are obtained by action of fermionic Gaussian unitaries on the vacuum state. The underlying reason of the classical simulability of fermionic Gaussian state is that under fermionic Gaussian unitaries, Majorana fermions transform according to this rule. So they transform. We have just a rotation under fermionic Gaussian unitary. We have just rotation of Majorana fermions by orthogonal matrix associated with the with this matrix H. And now let me define a covariance matrix for which can be defined for any state in Hilbert space, which is just expectation value of the commutator of two Majorana operators. This is a real antisymmetric matrix. If state is if state psi is a free fermionic state, fermionic Gaussian state, then the covariance matrix via Wick theorem encodes all correlation functions of the state. So it encodes all physical information about the state, and then under fermionic Gaussian unitary, using the rule how the Majorana fermions transform, we can see that the covariance matrix transforms via similarity transformation, which means that if we have some fermionic Gaussian state and then we are acting with fermionic Gaussian unitaries, we just need to transform the covariance matrix, and this will tell us everything about the properties of the system. So this is so that's why one can simulate the free fermionic systems with classical resources scaling polynomially with system size. And then, of course, I don't need to convince you that they are important from the point of view of physics. For instance, one can use them to solve transverse field Ising model. This Hamiltonian via Jordan-Wigner mapping can be mapped to a Hamiltonian which is quadratic in Majorana operators, and then it can be solved exactly. Okay, so one of the observations here is that while those two sets of states are classically simulable, the language which enables classical simulation is very different. Here, one needs to take care about the Pauli strings that stabilize the stabilizer state. So it is so-called tableau formalism. Here we care about the covariance matrix of the state. Okay, and now both things can be classically simulated, but the description is valid only if we are acting with free operations. If we are acting with operations that are beyond the set of free operations, then the description breaks down. For instance, it suffices to perform arbitrary rotation around z-axis of stabilizer state. In particular, and then particularly well-known example is rotation by angle pi 4, and then which is called a T-gate, and then acting with a T-gate on stabilizer state produces a superposition of stabilizer states, which is no longer a stabilizer state. This state is a resourceful state from the point of view of resource theory of non-stabilizerness. It's and then as when we act with more and more T-gates, we cannot really track the or the classical resources needed to track the state are scaling exponentially with system size. And then similarly, if one acts with fermionic Gaussian state or with beyond Gaussian operations, for instance, just swapping the qubits, we have state which is resourceful, which is no longer fermionic Gaussian. Covariance matrix no longer contains all of the information about the physical properties of the system. Okay, so
sorry, could I mean, you put the swap gate that from the point of view of the gate is very simple, but could I also think about, let's say, a unitary in which the Hamiltonian is no more quadratic and term?
exactly. So
okay.
so this this is, let's say, can be unitary operation generated. That's something that is, let's say, quartic in Majorana operator.
Okay.
So any sort of interaction in physical models is will be injecting fermionic non-Gaussianity to the state. Yes?
So the way that you check, the way that you check that this this is now non-stabilizer is that you cannot find a map from this Clifford map, or how do you check that this is not a stabilizer?
Yes, perfect question. This is my next line.
Okay.
So exactly. So what I want to do, I want to provide measures of these resources that will give me idea whether my state is a stabilizer state or is not stabilizer state, and ideally they will quantify some sort of distance of given state to the set of stabilizer states or Fermionic Gaussian states.
From your picture, it looks that they are different sets, but they are also intersecting. So
yes, exactly. They are intersecting, which means that there are Clifford operations which are also Gaussian unitaries. And then those are so-called Clifford match gates, and then they have a couple of interesting properties. Okay, so general quantum resource theories provide us with general ways of measuring the resources. For instance, just by looking at that, just by maximizing the fidelity of the state that we are looking at with all possible stabilizer states. If our state is a stabilizer state, then this overlap will be unity. We will find a stabilizer Clifford unitary that produces that state, and then we will have unity here. And then if we take minus log of that, we will have a measure that is faithful, invariant, and additive. Faithful meaning that it is vanishing, even only if the state is stabilizer state. Invariant meaning that it is not changing when we are acting with Clifford operations, and it is additive. One can show that minus log of that will be additive on product states. And in a similar way, one can define Gaussian fidelity, which is again maximum of the overlap with all possible Gaussian states of the state that we are investigating. The problem with these measures is that they are not really tailored to the problem. They involve maximization, which is a complicated thing. It is totally hopeless for stabilizer states because there is many of stabilizer states, and then the optimization problem here is a discrete optimization problem. It is also not easy for Gaussian states, although I don't know how not easy it is. Actually, I'm wondering how hard it is for Gaussian states. And then one of the reasons why people from many-body community became interested in these things is that recently there were proposed measures that do not involve any prohibitive minimization optimization procedures and can be used to quantify the non-stabilizerness or Fermionic non-Gaussianity, but particularly stabilizer entropy is a measure that just requires evaluating expectation values of all Pauli strings in the state that we are interested in. And if we calculate this quantity, we will see that it is vanishing even only if the state is a stabilizer state, and then it is increasing typically when we are acting with T-gate on the state. So it has all of the nice features of the non-stabilizer measures and non-stabilizerness measure. Technically, one can say that for pure state stabilizer protocols, it is a monotonic measure. And then similarly, one can construct measures of Fermionic non-Gaussianity, which have the properties that I have discussed. One particular way of doing that is just related to covariance matrix. And then I will discuss briefly this formula. So basically, the picture so far is that we have our many-body Hilbert space. We have the two groups of states that are simple from the perspective of the classical simulation, and then we have resources, non-stabilizerness, Fermionic magic or Fermionic non-Gaussianity, also entanglement and other properties of the many-body states, and then we can try to understand what are the properties of various physical phenomena on such a diagram. It is known there are examples of states that maximize, for instance, Fermionic magic and entanglement, but have zero non-stabilizerness. and vice versa. If we look at random free fermionic states, they will have zero fermionic magic, but they will have a lot of non-stabilizerness and a lot of entanglement. So to some degree, the axes here are orthogonal, but to what degree they are really orthogonal, it is not so clear. So let me now look more about on these fermionic magic resources and discuss this recent work with Paolo Stornati and Czech Turkeshi. So okay, so to quantify fermionic non-Gaussianity, we can use the either the Gaussian fidelity, or we can introduce so-called fermionic Gaussian rank, which is the minimal number that enables us to write our state of interest as a superposition of fermionic Gaussian states. Those measures require optimization over Gaussian states. And in this work, we propose a general ansatz for computable measure of non-Gaussianity. So we consider functions of several copies of the state with some, and then we trace that a replicated density matrix with a certain operator. And then if we want to have something which is not changing when we are acting on the state with Gaussian unitaries, this means that this operator must belong to what can be called Kate fermionic commutant. So set of operators that commute with tensor products of Kate tensor product of fermionic Gaussian unitaries. And if we take operator from that set, we will have something which is not changing. This measure will be manifestly invariant under fermionic Gaussian unitaries. Actually, the mathematical theory of fermionic commutant is not so developed. So while we have, we have some in this work we have presented some operators which belong to this fermionic commutant, and then there is the number of them is quite significant and is increasing with the number of the replicas of the state that we are considering. In the end, we have multiple of candidates for the measure of non-Gaussianity, each of them corresponding to different choice of that operator W. And now I would like to consider very simple idea, which is this FAF measure that was shown on the slide before. And then we can while the fermionic commutant provides a general framework in order to provide measures of non-Gaussianity that are invariant, we can just look at how the covariance matrix of any state is transforming when we are acting with fermionic Gaussian unitary. As we remember, this is the similarity transformation. This similarity transformation means that if we take the trace of transposed covariance matrix times the matrix, we will have due to the cyclicity of trace something which is not changing under fermionic Gaussian unitary. So we will have something which is Gaussian invariant. And then we can also see that if we have fermionic Gaussian state, due to the way how fermionic Gaussian states are obtained, this trace is equal to n. Therefore, we define fermionic anti-flatness FAF as this expression n minus 1/2 of the trace. We can take the trace to power 1, or we can take higher powers. This will give us different types of measures. Now, this very weird name comes from the fact that if we consider a canonical form of the covariance matrix, it can be brought to a form in which we have 2 by 2 blocks on the diagonal. Those eigenvalues here are called Williamson's eigenvalues. And then if we use that this decomposition to evaluate FAF, we will see that this is a expression which measures how flat the lambda I spectrum is. If it is totally flat, if the state is fermionic, it is totally flat and all of the lambdas are equal to unity when the state is fermionic Gaussian state. And then when the state deviates from the set of fermionic Gaussian states, this is no longer true. We'll see that FAF is bigger than 0. And the Williamson's eigenvalues go below unity and are no longer equal to each other. And then this measure has so it is Gaussian invariant. So due to this property of the trace. And then one can also show that it is vanishing even only if the state is Fermionic Gaussian state, and then also that it is additive on tensor product states, tensor products of states, provided that we have states with fixed parity. If we don't have fixed fermionic parity, then the measure is subadditive on the states. And then finally, it is nice from the point of view of experiment. It is just this FAF is just measuring properties of the covariance matrix, which means that in order to evaluate it, we just need to evaluate the covariance matrix, which is just composed of expectation values of products of Majorana operators, which can be done. And then there is polynomially many of those expectation values. This can be done experimentally.
Polynomially talking about where the one from Clifford is exponential.
Yes.
So why are they so different?
So Clifford states and Fermionic Gaussian states are very different. And it is so it is still exponentially hard in a sense that one needs to evaluate expectation values. So if you assume so let's but then I don't know why it is so
But
different.
that's
Like
the covariance matrix there, right? So that's
Yeah,
just linear in the number of.
yes, it is actually quadratic in the system
Yeah.
size because there is quadratic many expectation values of Majorana operators, and then we need to evaluate just those expectation values. This gives us covariance matrix of any state, and allows us to give us to get this measure which has these properties.
So, yeah. So you're saying if I measure the covariance matrix of quantum system for just one value of k.
Value of k is here in a, let's say, post-production.
Okay.
So we just
When I
need M.
measure the covariance matrix, then I can tell you whether that system is free fermions or not.
Yes. So that's the first message. If this measure will be 0, this measure is vanishing if and only if the state is Fermionic Gaussian state. So this will be set. Then the more complicated question is what are some monotonic properties when one does measurements. Also, and then and then also how it is related to other monotons of the theory of non-Gaussianity. I believe that it has quite nice relation with fermionic with Gaussian fidelity that I have defined above, but this is an ongoing work. Okay, but then yes, this is much simpler than stabilizer any entropy.
And it's also basis dependent?
So if I do local rotation, then so then various things happen. For instance, I will break the Z2 in yes. So local rotations will change it. Yes. For instance, so in that way, this
M is an expectation value, so it's not basis dependent.
Okay, but then so I'm not sure how to define. So what happens with SRE is that if one does, for instance, local rotations on each of the qubits, the value of SRE will generically change. For instance, I can take from a stabilizer state. If I do generic local rotation, this will be a not a stabilizer state. The same will happen with Fermionic Gaussian state. If locally rotated, not by Gaussian interest. So in that, okay. So okay. So let me mention another measure which also has the similar properties, at least in some limit, and it is called non-Gaussian entropy (NGE), introduced in that work, but also in earlier works it was considered in under various names. The idea of the other measure of non-Gaussianity is that one performs convolution operator. Convolution operation. Convolution operation is an operation which employs such fermionic convolution operator, which is operator acting on two copies of the system, coupling the two copies of the system. And then what convolution operation does for state rho, it is a tensor product taking tensor product of row with row, acting with this operator which couples the two copies, and then tracing out the degrees of freedom associated with the second copy. And then in this work, it is shown that convolution operation, when iterated many times, is converging. The state is converging to the set of Fermionic Gaussian states. And then in this work, it was shown that the entropy of this matrix, so even if we started with row, which is a pure state, after this operation, in general, it will be not pure. And then entropy of the associated density matrix is a measure of non-Gaussianity. In particular, if we take infinitely many times the convolution operation, we will find non-Gaussian entropy infinity, which is again a function of the eigenvalues of the covariance matrix, which was also considered in the earlier works. So in the same way as FAF, in FAF, I was able to, by taking the 2 norm of the covariance matrix, I was able to get a measure of non-Gaussianity. Here also, by considering eigenvalues of the covariance matrix, this is also a measure of non-Gaussianity. And then, in fact, in the limits of states which are close to Fermionic Gaussian states or close to Hard random states, the measures are related. And then one of the properties that is nice for FAF is that FAF is linear in the several copies of the state, while NGE is a more complicated function, and this sometimes helps to evaluate the FAF in some scenarios. Okay, so are there some more questions? Okay, so now I have my measure of fermionic non-Gaussianity, and I would like to understand how it is behaving for some systems. Okay, so let me start with product of fermionic magic states. When we have fixed fermionic parity, every state of 2 qubits and 3 qubits is a fermionic Gaussian state. In order to have a state which is not a fermionic Gaussian state when fermionic parity is fixed, we need 4 qubits. And an example of such a state is for instance this one. If we take tensor product of such 4 qubit states, we can evaluate the FAF very simply due to additivity. Thanks to the fixed parity, we will get something which is proportional to system size, and then depending on the angle that we have injected here, for some specific choices of the angle, this can be still a Fermionic Gaussian state. But this shows that already for a product state, so for a state with not a lot of entanglement, we can have extensively scaling measure of the non-Gaussianity. Similar thing actually happens for SRE.
This is not.
Yeah, this is product of 4 qubit states. So in that sense, it has little entanglement.
Okay, yeah, but it's not.
Yes. Yeah. So the point I'm making, one doesn't need a lot of entanglement to have already extensive amount of FAF. Then one can show that if we have a Fermionic Gaussian state, and then we act with a local gate, which is non-Gaussian, meaning that it is exponent of something which is not quadratic in Majorana operators, for instance, something which is quartic in Majorana operators, then just by looking at the action of that operator on covariance matrix, one can find that FAF is constant. So this is one nice property, that if we have something which is a Fermionic Gaussian state, we act with local operation, we have bounded amount of our measure of non-Gaussianity, and then it can be if we consider Hard random states. So we act on the 0 state with arbitrarily chosen unitary operation with Hard measure on the full unitary group. Those states have a lot of entanglement, have also a lot of non-stabilizerness, and one can calculate exactly that the expected average values of this measure of fermionic non-Gaussianity are also close to maximal. They are scaling with system size, with prefactor 1, with some exponentially small in system size correction. And then this can be shown by, for instance, seeing M as a random matrix. And then, as I said, this is so hard random states are example of featureless state which has a lot of bipartite entanglement. Stabilizer any entropy is nearly maximal, and also it is this measure of non-Gaussianity is also nearly maximal in that state. Then let me consider random matrix product states, which are states obtained in such a way that I am taking unitary with hard measure. I am taking unitary matrices. I am reshaping them as tensor which have two legs that I will interpret as the bond of MPS, and two indices that I will interpret as physical indices, and then I act on state 0 with such a random matrix product state. So it is a state which has fixed bond dimension, and then one can show that it is the same as particular type of Stargate circuit. And then one can evaluate this measure of Fermionic non-Gaussianity for these types of the setups easily for k equal to 1, because for k equal to 1 it suffices to perform the average over Clifford circuits, because the Clifford circuits reproduce the averages over full unitary group if we don't have too many copies of the state. So Clifford circuits for qubits are 3 design, which means that for k equal to 1, due to the 2 design property of Clifford circuits, the average over all possible unitary operations and average over Clifford circuits is the same. And we find that the deviation of this FAF from the maximal value for the hard random state, which appears when we take bond dimension that is maximal for given system size, is scaling as a power law of the bond dimension. So this gives one idea about what we can expect from this FAF if we do not have a highly structured system. And then also one can look at random evolution of FAF under random quantum circuits, and then find that it is saturating at timescales at circuit depths that are logarithmic with system size, so much faster than, for instance, entanglement entropy saturates, because it saturates the timescales that are linear in system size. And then it is similar to stabilizer any entropy in that manner. Okay, so let me now consider some more physical example, which is the Ising model. Ising model can be written as Hamiltonian, which is quadratic in Majorana operators, but it is an interesting model. It has a phase transition as we change the value of the field. We go between the 2 phases in which the entanglement entropy is follows area law, and then there is a logarithmic scaling of entanglement entropy at the critical point. But since the state at all values of parameter is Fermionic Gaussian state, if we evaluate FAF, we will find that it is 0. Now, if we take the Ising model and then we add such a term, which corresponds to term which is quartic in Majorana operators, so something which is already not a free fermionic system, we will again see, and this is so-called ANI model. We again see similar type of, for at least if this lambda is not too large, we will see again similar type of phase transition with similar features of entanglement entropy, but then the FAF will show non-trivial behavior. It is enhanced close to the transition, which is marked by the red line. However, it is not maximal at the transition. The extensive scaling that we have seen for random matrix product states or product states is the typical behavior. And then what happens if one looks at the subleading term? The subleading term in the scaling follows the typical collapses for the Ising phase transition. And then one interesting property of this model, which we were not aware when we started considering that, is that it features special point which is known as pressure emery point. in which the model can be solved, and as it was realized in 1980s. And then our measure is vanishing there, even though the entanglement is just smoothly changing. So it is somehow pinpointing the fact that at this point the state for fermionic boundary conditions in this ANI model becomes a free fermionic state. For open boundary conditions, instead of the extensive scaling, we have just very small value of FAF, which is not increasing with system size at this point.
Sorry, but it's just my ignorance. You said the model is not exactly solvable, except that the special.
Exactly. This is an interacting many-body system.
So how do you go to 1200 spins?
So this is ground state. So this is the MRG.
Okay.
So I should have. Yeah. So these are the MRG results. The earlier results were could also have been the MRG, but they were just the simulation, just the solution of the Ising model. Yeah, so this is interacting model. Then we evaluate that using the MRG, our measure. We find these types of behavior. This behavior, this vanishing at the critical point, can be traced to the critical properties of the properties of the correlation functions at the criticality. Since FAF is the combination of critical functions, if we have some universal scaling forms for the critical functions, as we do have for conformal field theories, we can understand better this behavior of this subleading term. Yeah, but then there is particular point that that when we do the MRG here, actually we learn that we could have just solved a free fermionic model. But then it was not. It is very not a fresh result, known from 80s since 80s.
This quantity seems useful to see if there are points in the parameter space where the model becomes free fermionic for some accidental reason, right?
For instance, that's one thing. The other thing is that if FAF is small, then this probably means certain things about the simplicity of the state from the point of view of fermionic Gaussian states. So here FAF is like 0.4, even though the system size is 640. So the FAF of her random state would be 640. Yeah. So, but then in order to I don't know yet what's the quantitative.
But then your DMRG will not work so well then, right?
Sorry?
I mean, if that was close to being a R state, then the DMRG will not work.
Okay, but
the dimension should be small.
Yeah. So, but that's one of the interesting questions. Like, to what extent DMRG's performance is dependent on the amount of entanglement, right? Then, and like, one can have states which have a lot of entanglement and little of FAF, and vice versa. So and then whether there are scenarios in which one has, one can try to build some computational methods that would use the fact that state is close to fermionic Gaussian state, even though it has a lot of entanglement, is like one of the open questions for me.
Maybe it's related to the fact that this point is quadratic. Let's say there is an hint that there is a quadratic theory in that point.
Yeah.
Because, I mean, the Jordan ligand is just one of the many mapping from qubits to fermionic degrees of freedom. There are others. So, let's say, I mean, if you have a system that is not quadratic in the Jordan ligand map, but could be quadratic in other maps, this quantity we recognize or not?
No, so this quantity is assuming that I am doing Jordan ligand transformation.
Okay, so if I take another transformation, I will have another quantity, or let's say.
Probably yes.
Okay.
Yes, unless I'm missing something. I would have to think about this a bit more. I was not thinking about that too much. So I was thinking more about just the Ising and then okay. So then one can also, with open boundary conditions, one can extract some features of this measure. But let me maybe not bore you with the details. Yeah. And now also now if we look at the ANI model, so the one that I was describing or the impurity model, which is just the Ising model plus one term, which is quartic in Majorana operators. And then we look at the properties of FAF as function of energy of eigenstate. We will see that this behavior is paralleling the behavior of entanglement entropy. Like while the ground state, so what I was considering earlier, has very limited amount of Fermi-Gaussian unity. As we go towards the middle of the spectrum, we get states which are close to the hard random states and expected results. And then it's the progression is slower when we have just single term that introduces the interaction, but it is still visible. And then if we look at the dynamics, if we have single term that is introducing non-Gaussianity, so we have this impurity model, we'll find ballistic in time increase of the measure of non-Gaussianity. While if we have extensively many terms that are interacting, we have extensive FAF already at times of the order of unity, and then a quite fast saturation to the maximal value, which however is occurring slower than in the case of circuits, but because at the time scales that are scaling more or less linearly with system size. Okay, so this brings me to my conclusions. So I try to convince you that so first of all, there are two classes of states that are simple from the point of view of classical computing, and then the theory of non-stabilizerness and measures of non-stabilizerness and measures of Fermi non-Gaussianity try to capture some features of the complexity of these states from the point of view of the simpler of arbitrary states from the point of view of simpler classes of states. And then in this couple of works, I was trying to understand the behavior of these measures in various scenarios. And the one that I was focusing on today was the Fermionic magic. And then the one of the interesting questions is to what extent one could use the insights that in some scenarios we have state which is close to set of Fermionic Gaussian states or stabilizer states to learn something more beyond the typical computational approaches that we use now. And also to what another interesting and fundamental question is to what extent those measures are let's say more fundamental than entanglement, or what's the general relation here between the different resources in physically relevant scenarios. Thank you for your attention.
Thanks a lot. More questions?
So if you have, a low magic state or a circuit with a low T-gate count, you can represent it in like sort of Pauli string space with an MPS sort of, right? Because like,
in some a little bit more convoluted way, yes.
Yeah, like a Clifford circuit would not produce superpositions of Paulis, but you could
Yeah, so general approach is that one if one has a circuit in which there is a lot of Clifford gates and some beyond Clifford gates, then one can trace the superposition of the Clifford states that is being produced. So Clifford gates will map the states of the superpositions from Clifford to Clifford, and then action, let's say with T gates, will increase the number of terms in the superposition, and one can try to simulate state in that way.
Yeah, and I mean, I think people have done this with like MPSs, but kind of written in some.
Yes, so
like,
with MPSs, there are a bit different ideas. Basically, the ideas, for instance, that one has MPS, and on top of MPS, one has Clifford unitary. The Clifford unitary can introduce a lot of entanglement. MPS has limited entanglement, but they can have a lot of magic. So it is quite powerful.
Yeah, well, it's just if you represent it in the operator space, that's the whole thing. Is that like the Clifford circuit is simple when you look at the operator dynamics, right? So,
okay, but then operator space is a little bit different story, I would say. So then SRE is not really telling us, and it's just telling us about the global properties of given state, not about the.
Okay, I guess I was trying to understand whether for fermionic Gaussian states, whether there's like an analogous property, because like the whole like the stabilizer stuff, like I think the original paper was called like Heisenberg picture of quantum computing or whatever, and it's like somehow like in the sort of operator space, the the Clifford circuits are simple. And then I was just wondering, like, what's the analogous space for fermionic Gaussian states? Like, is that known? Is there some other
Okay, so
object
it's
that I
the
should be looking at
second
where everything
time in
becomes
2
simple?
weeks that I was asked this question, and I'm not really sure how to formulate that. Like,
Okay.
so basically one could try to formulate the notion of fermionic magic in operator space. And yeah, and then introduce some measures of that would have the similar type of properties, and I'm not sure. I don't know how to do that precisely, but
Yeah.
okay, yeah. So what fermionic
But it's
Gaussian
like you would
unitar
need
is
some
to
kind of like, you would need some like efficient way of representing like, you know, products of more than two Majoranas, I guess.
yeah, but and then
but
there are even computational approaches like that. There is Majorana propagation, which is like just the analogous of Pauli propagation
Yeah.
technique. So there is a lot of
Okay.
things there.
Can you summarize again what's universal about this quantity that you looked at?
Universal.
Yeah, like at the
The
critical point.
universal, okay, in the sense that what happens, like let's say at the phase transition. That's
Yeah.
yeah. So here we have shown that if one takes periodic boundary conditions, then the subleading term encodes the transition.
Okay, but
and-
what kind of scaling exponent it has or things
Yeah.
like
So then the collapses here are so I extract the subleading term in system size scaling, and then this is the subleading term as function of the field for different system sizes close to the transition, and then I can do the rescaling, which works pretty well. So it features, and then this can be understood just from the perspective that in the end this quantity is just some combination of expectation values of Majorana operators. So at the transition, we know what are the properties of the correlation functions. They are vanishing as a power law. Of the criticality, we know that they are exponentially vanishing, and then those insights can be used to try to understand how this particular combination of these things behaves at the transition.
So you're not scaling the y-axis, you're only scaling the x-axis?
Here I am only scaling the y-axis, yeah. But then this is just the subleading term. The leading term, so that the overall behavior is such that it is enhanced at close to the transition, which is maybe a reasonable thing. But then we are very sad that it is not maximal at the transition, for instance. So we needed to resort to the subleading term to see the scaling. Also, if we consider this impurity model, then there is no extensive scaling. But then this is the behavior of this quantity close to the transition, because in the impurity model, basically it is already an interacting model, but still it is very close to the Ising limit. So then we have FAF, which is not scaling with system size. It has maximum, not at the transition, unfortunately. Its derivative with respect to the field has a logarithmic divergence at the transition. So this is my set of observations. Probably it would be nice to get some more universal picture with some boundary CFT, but I don't know whether FAF is the best measure for that. Maybe this non-Gaussian entropy would be better one.
I have a question. So, for example, in quantum chemistry, you take, your wave function, variation of wave function at the beginning as a single Slater determinant, and then you add another Slater determinant to improve the approximation when you have interacting electrons here. Typically, how much this quantity grows when you add other stuff, other Slater determinants?
Exactly. Yeah. So that's
you had something on the second slide, I think.
So that's what I have here. But then, so this is one part of the answer, but this is only the more favorable part of the answer. So here I am basically acting on a non-Gaussian, with a non-Gaussian gate on Gaussian state, which means that I am creating superposition of two Gaussian states, which differ only locally. Then, if I calculate FAF for this type of the superposition, then I will have only constant amount. But then, if I take two Gaussian states that differ a lot then I will have something which scales extensively.
Okay. So even if I put a little bit of another slitted determinant, but it's a completely different one from the other one,
Yes,
you're gonna get that F jumps to order N.
I believe so. Yeah.
More questions? Okay, if not, perhaps I can ask one more and then we go to the lunch. So, I mean, you gave initially a plot, not a plot, a figure of the entire Hilbert space, and then you said, okay, this is a resource free, this is a resource free. How complete do you think is that plot? So let's say, suppose that I don't know anything about fermionic Gaussian state. I know stabilizerness, so I arrive with a state with a lot of non-stabilizerness, and I would say, oh, this maybe is useful because it's non-classical. Then somebody tell me, no, because it's fermionic Gaussian. So how complete do you think is this?
So this is very this is approach in which we just take examples of classes of states which are classically simulable, and then we define resources, and then we have very general framework how to do that. Yeah, but then this is like, these are just necessary conditions. Like we need to have a lot of this, a lot of that in order to have quantum advantage. It is not the other way around. So, and then yeah, actually I don't know.
So do you think would be possible to find other corners that are classically simulable, or you think we are close to complete?
So for sure we are not close to complete, but then I'm not sure what to.
Okay.
So it would be good to have like a general class of states which can have a lot of entanglement as they can have.
Mm-hmm.
That is not neither of these classes of states. Yeah, and then one can build such a resource theory and then try to find some useful insights from that.
Okay. No more? Okay, let's go to lunch then.
Thanks.